Hi everybody. Today we're going to look at geometric series. So a geometric series is a sum of terms to position n in a geometric sequence. So if the GP was t1, t2, t3, t4 up to tn, where n was the number of terms, the sum of those terms would just be adding them up. And that gives us the series. So if we looked at a geometric progression where Tn equals AR intake 1 for n is greater than or equal to 1, Sn would equal to the first term A plus AR squared up to AR intake 1, where n was the number of terms in the series. So let's have a look at an example. 2, 4, 8, 16, 32, a very simple geometric progression. S1 would be 2, S2 would be 2 plus 4, S3 would be 2 plus 4 plus 8, S4 would be 2 plus 4 plus 8 plus 16, and S5 would be 2 plus 4 plus 8 plus 16 plus 32, giving us 2, 6, 8, 2, 6, 14, 30, and 62 if I can add. So we can simplify the equation for Sn. So if we take Sn, which is just A plus AR squared plus up to AR intake 2 plus AR intake 1, and we take a second sum where I've multiplied this by R. If I multiply this side by R, I get RSN. And if I multiply this side by R, I get AR plus AR squared plus so on and so forth. And as you can see here, if we subtract them, Sn take that will cancel, that'll cancel, all the way down to the very last term, second last term, which cancels, and we're left with A and ARN. So that take that, you end up with this line here. If you factorize both sides, you end up with this expression. Divide both sides by 1, take R, you end up with the series is equal to A multiplied by 1 take R to the power of n divided by 1 take R, where obviously R can't equal 1 because it would make the function undefined. And typically we use this equation if R lies between -1 and 1. Now similarly, we could have done this in the reverse order, this equation minus this equation, which I've done here, and if that's the case, you end up with that, take that as your solution, which I have here. Similarly, factorize again, and you'll end up with this equation here, again, where R can't equal 1, because the function will be undefined. And typically we use this if R is less than -1 or R is greater than 1. Now, one thing to note is that if R lies between -1 and 1, the function will converge as x tends to infinity, and it will diverge at the other end. Similarly, if R is less than 1 or greater than 1, it will diverge as x tends to infinity. Now, given that the series converges if R lies between -1 and 1, we can find the value that it converges to from the equation A on 1 take R. But we can't do that if the function diverges. So let's look at some cases. Here's the series 64, 32, 16, 8, 4. It's halving each time. R lies between R lies between -1 and 1, indicating it's going to converge to a specific value. So if I do the substitution, I end up with this equation here for Sn. And if I substitute in 15 for n, I'll get 64. If I continue this process to infinity, I'll end up with it diverging to 128. All well and good so far. If I have a sequence which diverges, I'll have a series that also diverges. In this case, S15 will equal 65,534, and as this keeps getting bigger and bigger, so will the sum to infinity. Interesting case where R equals a negative value. So in this case, I've got the sequence 2, negative 4, 8, negative 16, 32, so on and so forth, where the sign changes each time. A will equal 2, R will equal negative 2. And if I substitute this in for S15, it'll be 21,845.33. If I went to 16, it would be a bigger value, but negative. And that would be because I'll have a positive value on the top, because that will make negative 2 to the power of 16 is a positive value. And the negative 1 isn't going to change that, and nor is the 2. And the bottom, the denominator will be negative, positive divided by negative will be negative. Which leads us to this interesting observation: as x tends to infinity, the answer will tend to negative infinity if n is even, and as s tends to infinity, it will also tend to infinity when n is odd. And we don't typically think of positive and negative infinities for dependent on whether n is odd or even. So it is a bit of an interesting case. But I will leave that to university mathematics to investigate positive and negative infinities further later on. So there you go. A bit of a quick look at geometric series. Thank you, everyone.